everyone. Today I will present our work called S3PO-GS, Outdoor Monocular SLAM with Global Scale Consistent 3D Gaussian Point Map. This work is from our 3D Agent World Lab at DZ, and it is accepted to ICCV2025. Let me start with the motivation. Outdoor scenes are very complex and often unbounded. They include large viewpoint changes, which make pose optimization and reconstruction very difficult. Purely visual methods usually fail here because they do not have strong geometric priors. Existing 3D GS SLAM systems such as PhotoSLAM, MGS SLAM, or OpenGS SLAM rely on separate tracking modules and often suffer from scale drift. This drift becomes worse under large motions and makes both localization and mapping less accurate. Pre-trained monocular depth or point map models, like Depth Anything or Mass 3R, can provide geometric priors, but they usually do not keep scale consistency across frames. This limits their use as reliable constraints. So our core idea is to develop a 3D GS SLAM framework that introduces usable global geometric constraints under only monocular RGB inputs. We want to suppress scale drift and achieve stable, accurate localization and reconstruction in complex outdoor scenes. On the Kitty dataset, for example, our method can maintain robust camera tracking and high-quality novel view rendering, even during sharp turns and large viewpoint changes. Now I will explain our framework. The system starts with the first frame to initialize the Gaussian scene. Then it runs frame by frame. Each new frame begins with pose tracking, and keyframes also start mapping. For tracking, we build a triple correspondence among 3D Gaussian, pre-trained point maps, and the new input view. This gives us fast and stable pose optimization while keeping global scale consistency. For mapping, we design a patch-based scale alignment module. It performs bidirectional correction between the pre-trained point map and the evolving Gaussian scene. This ensures that both the poses and the scene are globally scale consistent. Let me give more detail. For each new frame, we first render a 3D GS point map from the viewpoints of nearby keyframes. Then we do per pixel matching between the current frame and these keyframes. Using these pixel correspondences, we link the current frame to the rendered point map and obtain 2D-3D correspondences. From these correspondences, we estimate the initial pose with PNP and Ransack. After that, we refine the pose by minimizing the photometric error in the differentiable 3D GS rendering pipeline. A key part of our framework is patch-based scale alignment. The motivation is that the pre-trained point map has useful geometry, but its global scale does not match the Gaussian scene. So we must correct this. We divide both the Gaussian point map and the pre-trained point map into patches. Then we select candidate patches with similar distributions. Inside these patches, we normalize and select accurate pixels to compute the scale correction factor. We repeat this process until the scale factor stabilizes. In the end, we get a globally scale-aligned pre-trained point map. This aligned point map becomes a strong geometric constraint that improves both mapping consistency and tracking stability. Now, the result. On 3 outdoor datasets, our method achieves significant improvements compared to previous 3D GS-based and NeoRF-based SLAM methods. If we look at the rendering comparisons on Waymo, Kitty, and DL3DV, we can see that our method produces images with higher quality. The details of vehicles, streets, buildings, flower beds, and eaves are much clearer. The depth maps are also more accurate in complex areas like tree branches, roadside vehicles, and pillars, and they are smoother in large flat regions such as the ground. For pose trajectory comparisons, the results also show that under large viewpoint changes, other methods often suffer from significant drift. In contrast, our method demonstrates much stronger robustness. This means our approach can maintain consistent tracking even in very challenging outdoor sequences. To conclude, S3PO-GS introduces global scale-consistent Gaussian point maps into monocular SLAM. With our new tracking and mapping modules, we can suppress scale drift and achieve stable, accurate localization and high-quality rendering in outdoor scenes. Thank you for your attention.